The first law is it's kind of two things. It's like if something is in motion, if a body is in motion, it will remain in motion
Mhm.
until something is acted upon it. So a possible analogy is watching a ball roll.
Mhm.
So maybe if you played pool, then you would see this, like the ball rolls and it doesn't stop rolling until it hits a corner or an edge, or maybe
Yeah.
ice. If you've ever seen ice, it just seems to slide forever. Uh, the truth is, though, is
Mhm.
that most things do have forces acting on them, which is what causes them to like um, not remain in motion.
Yeah.
So are you driving currently? Are you a driver
Yes.
now? Okay, so if you were to like if you were to let your foot off the brake and the car would roll forward, it may eventually come to, or if you were to give it some gas, it would go forward, but then it might eventually come to a stop because there's things
Mhm.
internally and then on the road that are causing it to like prevent it from continuing forever. Um,
Yeah.
so that's kind of the first part of it. The other way of looking at it is if a body is at rest, I think this one is easier. It will remain at rest until something acts upon it.
Okay.
So if an object is not moving, it won't suddenly start to move.
Mhm.
So there's no like spontaneous like, oh, now it's moving kind of weird thing. It's either moving and it stays in motion, or um, it's not moving, so it won't automatically start moving.
Mhm.
Is that Does that clarify that if that was unclear?
Yeah.
Okay. Second law is much more straightforward. The second law is the equation you're going to use for a few problems. F equals ma. I assume you saw that in class.
Yes.
Okay, so F is the force, and the units of force are in newtons.
Mhm.
Okay, and M stands for
Mhm.
mass, and that's in kilograms. And then acceleration is in meters per second squared.
Okay.
Hopefully you saw that in class.
Yeah.
Okay. Okay. So a newton, 1 newton, is 1 kilogram meter per second squared.
Mhm.
And that probably doesn't mean much. It didn't mean much to me the first time I saw it, but in physics, there's this importance of units that we're discussing right now.
Mhm.
Okay. It looks like your worksheet has some problems for both of these, maybe. But let's go to the third law, and then we'll go to some problems, I guess.
Okay. I'm not entirely sure if the actual like work problems will be on there because in class we've been reviewing and it's mostly talked about like the analogy problems.
Okay.
So like he hasn't really mentioned a lot of formulas. So
Okay. We're gonna talk about we'll do some of everything, I guess. So the third law is that it has to do with like interactions, and it talks about that there are forces that are equal and opposite.
Mhm.
And I don't find any of these very helpful, like with the words, But like if you push against the wall pushes back.
Yeah.
If you put a book on a table, the table pushes back on the book.
Hmm.
And so in some weird way, like the ground pushes back up on you, preventing you from going into the surface of the earth.
Okay.
This is all conceptual, by the way. This like, and these are, I mean, these are truths, they're laws, they're things that we believe to be true in this class, in this area of science, but you can't physically, like you can't see the force pushing up from the
Hmm.
ground into your feet. You just like you can't see gravity pushing down on you, but when you jump up,
Yeah.
you don't stay up in the air, you come back down. That's, we call that gravity.
Hmm.
So that's my, I guess that's my like 8-minute introduction. Um, let's look at your problems and see if we can clarify anything on there. This is very conceptual, which I hope is good,
Hmm.
but it's probably gonna be more of a like us talking and not so much us doing any problems today.
Okay.
Okay, so Julia's mass and Matthew's mass, that's me. Our mass is like, our masses are different, okay, but your mass is the same whether you're on Earth or I don't know, Mars, we'll say.
Okay.
And in your mass, like for lack of a better like description, it's like the stuff inside you. Like your body is your mass.
Okay.
Your weight takes into account gravity. But
Okay.
your mass, like the stuff inside you, if you go to another planet, if we could do that, it's the same here and there. These words are often used incorrectly together. They're
Yeah.
often interchanged incorrectly. And the rest of your life, unless you go into this world, no one will care. But in this class, your mass is the same everywhere, but your weight changes depending on gravity. Now,
Okay.
my mass is different than your mass, but it's the same principle. It's the same on Earth uh, or Mars. But
Okay.
the weight, and it's a simple relationship. Your weight is equal to mass times gravity.
Yep. Okay.
Okay, so when you go to a scale, the scale measures weight.
Okay.
Scale measures weight. So and you go to the scale. If you do, you get your weight, and
Okay.
then your mass is not. It's included, but it's not. It's based on gravity.
Okay.
Please interrupt me if that's unclear.
Okay.
Number 2 is a little bit harder for me to answer. Just to be clear, physics is not my like main area of expertise. I can help with all this, but this one's gonna be a little bit tough for me because of the way this is written. Um, would it be easier to lift a heavy box here on the Earth or on the moon? So the gravity on Earth and the gravity on moon are different.
Hmm.
And they're different numbers. Like if we want to assign a number, this is like 9.8, and I actually don't know what the gravity on the moon is. Let me look real quick. Gravity moon. Gravity on the moon is 1.6.
Okay.
So the weight of something, so the heavy box, let's just say it has a mass of 2 kilograms.
Okay.
Its weight on Earth is mass times gravity, which is 2 times 9.8. its weight on the moon is still m times g, but the mass is the same, but the gravity is different. See how these
Okay.
are exactly the same except for that number there. So what this problem is asking you to understand is that the mass is the same, but because the gravity is different, it will be easier. So it's easier here. It's easier when gravity is less.
Yeah.
Maybe you watched or are familiar with like NASA explorations to the moon, people jumping on the moon saying, you know, it's easier to jump up and down. If we were able to get to Mars, you could jump 9-10 feet in the air or more because of the gravity that's different. And that's
Oh, okay.
because there's less gravity. So the more gravity there is, the harder it is to lift something.
Okay.
All right, let me look at the next question here. Number 3, we have answered in great detail. You're going to know this right away. If you travel to another planet that is much larger than the Earth, would your mass still be the same?
Yes.
Your mass is always the same. Doesn't matter whether you're here or there or anywhere, your mass is always the same. Your weight would be different though.
Yeah.
Your weight is different because your weight is,
Gravity.
yes, gravity is different. Now it's generally assumed that if this is a large planet and this is a small planet, that gravity is more on the large planet. Gravity is less on small planet.
Okay.
And these are all relative. Like if Earth is the large planet and the moon is the small planet, we just saw that it's 9.8 versus 1.6. If Earth is the small planet and Jupiter is the large planet, the gravity is much larger on Jupiter.
Okay.
Is that okay? Is that clear?
Yeah.
Okay, so for number 5, we have to talk about the units of weight in SI and US. So weight, again, weight is
Okay.
mass times gravity. So in SI units, the weight is in newtons. In US units, the weight is in pounds.
Okay.
So when you get on a scale, it's telling you your weight. If you go and weigh something because you're going to ship it, that's telling you the weight. So pounds is weight. Pounds is weight. So the answer to this question in short is 1.5. It's not asking for anything else besides that.
Okay.
Is that okay? I mean, because it's slightly different than what you wrote down, and I want to make sure you're comfortable with the change.
Yeah, that makes sense.
Okay. 6 is a good question because it finally gets into this important concept a little bit with some numbers. How much would a 115-pound girl weigh if she traveled to a planet with 1/3 of the Earth's gravity? Okay, so what is your weight? what is not, I'm sorry, not what is your weight, Julia? What is the weight of this girl?
150.
Pounds. Okay. Now her weight, just as you wrote here, is equal to, weight is equal to mass times acceleration, which ends up being gravity. So this 115 is this number here.
Okay.
And on Earth, gravity is 9.8. Are you allowed to use a calculator on this?
Yes, I believe so.
Okay. So go ahead and divide 115 by 9.8. If not, you can round it up to 10.
Um, 11.7.
Okay, so the mass, oh, you know what, I'm sorry. I messed up something in a previous problem. I'm so sorry. I need to back up. I'm so sorry. I messed up this previous problem. We need to go back and talk about this. I got sidetracked here. So let me just jump back to 5, and then we'll come back to this. So I apologize. Your pounds is your mass.
Okay.
And that's where I made the mistake here. The SI unit for mass is kilogram, and the US unit is pounds. Your weight, in SI units is newtons, and it's slugs in US.
Okay.
So it's an important distinction here. So your weight is M times G, excuse me. Your mass here is 1.5, gravity is 9.8. So it's 1.5 times 9.8.
Okay.
Apologize for that mistake there, because that hopefully that doesn't. So the when you multiply those together, you get 14.7. Is that okay? So pounds
Yeah.
is your mass. When you go to the scale, pounds is your mass. All right, number 6.
Okay.
Number 6. So here in number 6, they're giving you the mass. They're telling you this is your mass. Okay, so your weight on Earth is 115 times 9.8.
Okay.
Okay, so you could calculate that. Okay, but they're telling you, let's do that. Let's actually get that number, 115 times 9.8. Okay, so did you get that number?
Yes.
Okay, so on another planet, your mass is still the same, right? Your mass is still 115, but the gravity, it's not 9.8. Your gravity is 9.8, or 1/3 of 9.8.
Yes.
So 1/3 of 9.8 is about 3.3. So the gravity this time is 3.3. And that's your, that gives you your new weight on this other planet of 376-ish.
Okay.
So if you were to take this 376 and divide it by 1127, you're going to get about 1/3.
Okay.
Is there anything you'd like me to cover again or explain again on this?
I don't think so. It makes sense.
Okay, so mass is always the same. That's the summary so far. Your weight depends on gravity. That's the summary of these 6 problems that we've done.
Okay.
All right. Okay, so now we're going to go to Newton's third law. Is that okay?
Yeah.
So I'm going to draw a few pictures. Hopefully it's clear. A soccer player kicks a ball. So here's a ball, and assume that this is a foot. Okay, the foot is applying a force to the ball.
Yeah.
The ball provides a force back.
Okay.
So it's not that the ball, so we use the word kick, but really it's a force on the ball. The ball provides a force, and this is important to use these words, equal and opposite.
Okay.
Okay, but that's only if it doesn't go anywhere. So we have to, so if it doesn't go anywhere, it's a force equal and opposite, but we assume the player kicks it. So it actually goes into motion. So I'm sorry, I'm not trying to pick on your word. I'm just trying to think of a better word. A soccer player like strikes a ball, the ball strikes the player. I guess the ball kicks the player is okay.
Okay.
But there's a force backwards. Like it's not as if but this is a little bit strange because these are considered in motion. So the force opposite isn't as big as the force towards the ball. Otherwise it wouldn't go into motion. But I don't, maybe did you just copy? I mean, I assume these are correct, or you copy these down from what the instructor wanted.
Yeah.
Okay, so they're all correct. Like you just, it's kind of like rewriting the sentence backwards at the and with the words flipped. A tennis racket strikes a tennis ball. The tennis ball strikes the racket. There's nothing there. Newton's third law, though, generally refers to things that aren't in motion, but it can refer to things that are in motion, I guess.
Okay.
Okay. I think this will make more sense when we look at 4.
Okay.
Although some of these scenarios, I mean, maybe you don't know anything about. I have no idea. When you and that's why they could be difficult to determine. A rifle fires a bullet. Okay, so the bullet goes forward after you're done, and the person, they go backwards.
Okay.
Oh, I'm sorry. The rifle pushes backwards, but the person does not. Okay, I see. These are so odd. Okay, so imagine that's the rifle. It pushes backwards, but the person doesn't move. Like if you've ever fired a rifle, you put it up against your shoulder and it doesn't, you don't move. I mean, it could move, but it generally just stays there. So that's why they're equal.
Okay.
I mean, these are all equal and opposite. I mean, this is the third law. The third law is that they're equal and opposite. So they're all the same. Like they're. Let me just double check here. Third law. Yeah. So they're always equal and opposite. So that like the question 5 here about a bat striking a ball. It's always equal and opposite. So let's maybe draw a picture, I guess. Maybe this seems okay. A bat, ball comes in, ball goes that way, and there's a force backwards on the bat.
Mm-hmm.
So it's always equal and opposite is Newton's third law.
Okay.
I'm tempted to provide some other examples that are a little bit more. Yeah, but these all are the same. They're all equal and opposite. I mean, there's not much more to say.
Okay.
Would you like some more examples of these that maybe aren't quite like these, or what?
Yeah, that would be great.
Okay. Some of the examples in physics are kind of they're difficult because they're sort of weird scenarios. But have you ever jumped from a high distance?
Yes.
Okay, so when you hit the ground, and this will make more sense. When you hit the ground pushes up with the same force you're coming down with. So sometimes it hurts when you
Oh.
jump on the ground because
Yeah.
the exact same force that you're using to get down comes right back at you when you hit the ground.
Oh, okay.
Some people, again, I'm sorry for only thinking of sort of negative things here, but like sometimes people will hit a wall and they break their hand. And it's because the force that they're striking the wall with comes equal and opposite back to their hand.
Okay.
And that's why their hand breaks, because the force is nowhere else to go except into their body and breaks their hand. I'm sorry, these are horrible, but these are the real scenarios.
Yeah, it makes sense though.
Okay. So this is why you don't want to hit things. Like if you hit something, you hope it moves.
Mm.
Because then it's that everything's being there's things that are transferred. Like when you hit a pillow, the pillow absorbs, the strike, moves around.
Okay.
So eight's kind of more like the scenario. This is what we expect to happen. Like when there's a collision, which is a lot of what mechanics is in physics, collisions. You have a large player striking a smaller player. Okay.
Mm-hmm.
And they hit each other. Okay. So this is like the start. They're both going this way, and then they collide. So the next image here is them colliding. Okay. And they're briefly there. Okay. And then later on, what would you expect to happen? You actually expect the larger person not to go anywhere, but the smaller player to go to the right.
Yeah.
So in this collision, the reason it's not equal and opposite is because one person's traveling off to the right at the end. If they were equal and
Yeah.
opposite, there would be no motion.
Mhm.
So because they come together, and we assume that, maybe we need to make this one a little bigger here, this arrow a little bigger for the big guy and the little guy, or the big girl and the little girl. They come together, okay? And then
Mhm.
because this person has a bigger force, you go that way, to the right.
Yeah.
Does that help with understanding this? So it's like if you were to draw these two arrows, you have a bigger one here. The little one kind of takes away some of it, and then that what's left over is what gets transferred to the
Mhm.
person. Did you ever play tug of war in school or something?
Yeah.
That's the better example here. When you have a team of big people on one side pulling really hard, and you have, little people on the other side, which direction do they go?
To the left.
Because these guys are pulling that way at the big force, they're pulling this way with a little force. What's the net result of that?
The
That way. That's
left.
the net result, like you said. And that's sometimes an exam question what they ask about that.
About net force.
The net result of a tug of war.
Okay.
It's the same thing as the collision. It's just a different scenario.
Okay.
We have some time remaining. What else would you like to look at?
Today in class we were talking about let me look at my notes. So it was okay, so one of them that I think that would wrap this up would be just all the laws of motion for
Which
like
one? Say that one more time. I'm sorry.
it just says Newton's laws of motion, and then it talks about like net force, and
Okay.
then if we could also go over friction.
Okay. So we just talked a little bit about net force.
Okay.
And it's kind of, we can make these a little bit more simple. Let's say you're pushing on a box and you're pushing with 10 newtons, and I'm pushing on a similar box with 6 newtons. Which direction is it going to go?
To the right.
To the right, because this one's bigger. So the greater force, this is the summary of that, the greater force produces the direction of motion. And that's so we can make any example you want, as long as whichever one is bigger, that's the direction it will move in.
Okay.
Okay, so now we can talk about friction.
Okay.
If you were to push a box to the right with 10 newtons of force, it doesn't matter how much, it will move right. As long as, and this is the important part, as long as the force exceeds friction.
Okay.
So if there's a friction force here, if there's a friction force on this box that's 10 newtons, it won't move. So this is U. And then if there's friction, it's generally drawn on the floor here. If friction is equal to 10 newtons, there's no motion.
Yeah.
But if there's less than 10 newtons, so if you have 10 newtons here and friction is 8 newtons, what will happen?
It will go to the right.
It will move right. Now here's the kind of the interesting thing about friction is the friction force is as big as it needs to be. And I'll try to explain what that means here shortly. So
Okay.
it's a little bit kind of gray. It's not as clear. So let's just say, if you've got carpet, let's just say that the carpet is up to 20 newtons of friction.
Okay.
So if you push with 10 newtons, again, the friction force is 10 newtons.
Mm-hmm.
But if you push with 12 newtons, the friction force is 12 newtons. But let's
Okay.
say you push with 25 newtons, the friction force is limited to 20 newtons. So it's up to that. Like whatever it is, it can't exceed it. So there's this idea that there's these two ideas of friction. There's like kinetic and static. And basically,
Yeah.
friction is as big as it needs to be until you get it moving, and then it's constant.
Okay.
Is there anything else you would like us to look at tonight or talk about?
I think I still don't totally understand net force. Like, I think that's the most confusing part of this to me.
Okay, so your net force is where you add up all the forces.
Okay.
And to keep this simple, like you assume they're all in a straight line.
Okay.
So let's say you're pushing, well, actually, let's do another box situation. Here's a box and Julia is pushing 20 newtons and Jack is pushing 15 newtons and your mom's pushing 30 newtons. Which way will this box go?
To the right.
Because 20 plus 30, 15 is greater than 30.
Mm-hmm.
Okay. But now all of a sudden, let's say your dad gets involved and he adds he goes 40 newtons. Now, which way is it going?
The left.
To the left, because there's more force to the left than to the right.
Okay.
So whichever direction there's more force, that will be the direction that it moves.
Okay.
So that's net force. Now we typically talk about it in like the horizontal direction, like you see here, but you could also talk about it vertically. So let's say there's a box and you're pushing up on it. You're providing 10 newtons and someone's sitting on it. Oh, sorry, it's a very bad analogy, but there's a force down on it that's 20 newtons. Which direction is it going to go?
Down.
Down. And if I add another 10 newtons, what will happen?
It'll stay at rest.
It'll stay at rest because the forces are equal and opposite.
Okay.
So the net force tells you the direction of motion. Net means you add them all up. So like sometimes in money, we talk about net like additions and subtractions. It's the same with forces. Generally right is positive and left is negative.
Mhm.
So whichever one you have more of, you're going to go in that direction. So if we go back to this previous example here, with you, your brother, your mom, and your dad, it would be like 20 plus 15 minus 30 minus 40. And that adds up to negative 35, which is left because it's negative.
Mhm.
But intuitively, oh, there's more here than there's more on the right, more going left than going right. So it must move left.
Mhm.
Let me see if there's any other problems I can find that'll maybe help here. All right, so here's a picture. I'll have you jump in and try to answer these. Okay, so oh, they give you the answer. Oops. Let's just look at it then together. So Billy and Susie here, they're carrying a piano or pushing a piano. Susie's going right, Billy's going right. That's why they add them up.
Okay.
Okay, let's look at another one here. This one I will not put the answer in. I want to try to do a better job of that. Here you got two animals pulling on a rope.
Okay.
10 newtons left, 12 newtons right. What will happen?
It will go to the right.
It will go to the right. All right, so here is, and these are considered unbalanced. I don't know if you use that word much in class, but unbalanced means they're not equal to each other.
Okay.
So this is the next one here to look at. And you've got a person going right, person going left. This is kind of like the large person running into the smaller person. What will happen after they collide?
The little one will have more of an effect.
It's gonna go right because because this is bigger than the 1 Newton. Okay. What else? We got a few minutes. Up to you if you want to keep going. I'm not sure I can say any more on these topics, but if you got some more stuff, we can certainly talk about it.
I think I'm good actually.
All right. So I will send the notes and the screen recording out in a little bit. Thanks so much for scheduling, and I'll see you next time.
Okay, thank you.
Have a great night. Bye now.
Bye.